this scalar function in front. And what that means is we will have to take that scalar function and evaluate it along the surface, along the vector function. So we're going to plug a vector function into a scalar function. We've done that before as well. I told you that seems weird to plug a vector into a scalar function, but we can do it. Just plug whatever the x component here is, we plug in for the x. Whatever the y component is, we plug in for the y. Whatever the z is, we plug in for z. I think an example will probably help us try and understand what's going on here. So find the surface integral of this scalar function. This is our scalar function right here, f, with respect to capital S. So we would say with respect to surface area, right? With respect to surface area. And that integral I just did a second ago, I just erased, we would say that this is the integral of the scalar function f with respect to, do you all remember what little s is? Little s? What did you say? Arc length, very good. So this would be the line integral with respect to arc length. This d capital S is the integral with respect to surface area. So we're doing like little infinitesimal surfaces, adding up the values along that surface. All right, so now I need to draw the surface, right? I need to draw that surface. Well, wait a minute. Isn't that, oh, wait a minute, you have to read this carefully here. What am I asking for? Find this where S is what? The part of the unit sphere that's above that cone. Not part of the cone, it's the part of the unit sphere that's above a cone. All right, so let me draw the unit sphere first. We need to figure out what S looks like. So here's the unit sphere, radius 1. I'm not going to put it on there. And then we have a cone. This cone right here, you have to know what that looks like. All right, so think about it just for a second. If you plug in 0 and 0 for x and y, what's z? 0. Okay, so here's the origin. Right? And then, let's see. Let's imagine that y is 0, okay? If y is 0, I don't want to get my grid out, but you got your x, your y, your z, right? If your y is 0, then you're only looking at like a cross-section this way. What does this look like if y is 0? What's the square root of x squared? X, but it plus or minus, so absolute value of x. It's absolute value of x, so it looks like a v in one direction. And then if you let x be 0, what does it look like? Absolute value of y, which is a v in the other direction. So basically your cone looks like this. Punches through like that, somewhere right, and that cone goes forever, but I'll just put a top on it up here. Okay, so that cone goes forever. What we are looking for is the surface area, not surface area, sorry, this integral over the surface S, where S is over here. Hopefully y'all see this. It's like the top of a little snow cone almost, right? It's just like the top surface of a snow cone. Yes?
Would that be the volume of that if we took the integral?
No.
That area?
Nope. So what this is I'm saying go to all the points on here, right? Like let's just say go to that point. Tell me what the x, y, and z coordinate are. Multiply the x, the y, the z together, and you're going to get a number, right?
Okay.
Okay, hold that number. Now move to the next point and do it again. Hold that number. And do that over the entire surface. Add all those numbers up, and that's going to be what this gives you. Okay. It's the sum of the value of that function along the entire surface. The sum of the value of that function over that entire surface. So if this function is the density of that surface, then this integral will give us the mass of that surface.
Oh,
okay. Yeah? We need to draw that. We need to draw that. That is part of a sphere, isn't it? So do we want to try and get this to a shortcut, or do we want to attack it just like brute force the other way? I'll make the decision. We're going to go brute force because we did the work last class. All right? We did a bunch of stuff with sphere at the end of last class, unit sphere. So recall from last class, that we had found the parametric function that draws a sphere. It's r of uv equals cosine u sine v, comma, sine u sine v, and then last one is cosine v. Right? That will draw me the unit sphere. Yes? We did that last class? Look familiar? Does it look familiar? Yeah, okay. That draws me, but I need to put restrictions on u and v. Do I want to draw the whole sphere? I don't want the whole sphere, do I? So go back to when we were first talking about spherical coordinates. You stand at the origin, looking down the x-axis, or no, looking straight up, right? That's the way spherical goes. This angle is what? It was the phi, right? And this one was the theta. For us, what's the theta and what's the phi here? V is the phi, right? So the V is the phi, and the U is the what used to be theta for us. Again, we talked about that last class, all right? So if I wanted to draw this, let's see. How far do I come down? 45 degrees. How do we know that? Because it's the absolute value, which we said was like x, and that's a perfect 45-degree angle. So I want to come down by pi over 4. I'm going to use radians, right? So I want to come down by pi over 4. So from 0 to pi over 4, that's my restriction on v, right? And then I want to be able to swing around, right? And back and forth like this. I'm getting dizzy, right? Won't that draw me that up there? Whew. Combination of the bright light in my eyes and tracers. Okay. Y'all see that? All right. That should draw me S, right? This draws me S right here. That draws me S. Okay, I'm going to need now to take this function and evaluate it along this vector surface. That means I'm going to replace this x with this y with this z with this, right? And then the ds is from the previous section is the magnitude of the cross product of the partials. Now, I could go and start taking partials, right? And then cross product and then magnitude, but we did that in class last time. If you look back in your notes, ... what was the magnitude of the cross product of the partials? It turned out to be super nice. Anyone got it? Sine V. Sine V. So there's a lot of ... work that I'm not doing here because we already did it. So I'm using this formula right there, right? I'm using this formula right here that I need to do the double integral over the d. The d is the domain. That's this right here. That's our domain, right? Our domain here cannot be seen in here. It's not on the ground, right? It's not the xy plane. It's a background clock, 2 clocks. Yes?
Real quick, if we come across like a problem like this on the exam, could we just know that RU crossed with RV is equal to sine V and that...
If it's a unit sphere, I'm okay with that.
We can just know that, we don't have to...
Yeah. Do you know what it becomes? Anyone know what it becomes if it's not the unit sphere? If the sphere has a radius of rho?
Would it be rho sine V?
Do y'all remember the Jacobian, what we had to do anytime we went from Cartesian to spherical, what we put it at the end? What was it? Yeah, the Jacobian determinant thing. Do you remember what it was? No? It's this. So if you add a row into this, row here, row here, row here, this will become that Jacobian determinant thing. That's a different conversation. Let's not get into it. So on the test, yes, if you said, hey, yeah, unit sphere, I know what this is. All right, where are we? We got to do this double integral over d. Here's our d. We've got to evaluate the scalar function. This one right here, we have to evaluate that scalar function along here, and then multiply that by sine v and then dA, right? put it right here. So the double integral over S of the scalar function f of x, y with respect to the surface area will be the double integral over d. Let's go ahead and put the limits of integration. 0 to 2 pi, 0 to pi over 4. And now, the scalar function evaluated on the surface. So that's x, y, z. That's x times y times z. Yes, it's going to be ugly. Cosine u, sine v, sine u, sine v, times cosine v. So everyone understand that's x, y, z? X, y, z. And then now I need the magnitude of the cross product of the partials, which we said is sine v. And then d, dv, du. And now I get to do that integral. So that becomes, I'm just going to clean it up a little bit, 0 to 2 pi, 0 to pi over 4. I'm getting a headache. Usually when I do math, my headaches go away, but today it's the other way around. Yeah, no, we can't afford that. Okay, I'm going to underline everything with u's in it. That's it, right? That's the only thing with u's? Okay, so I'm going to put those next to each other. I'm going to put the sine in front of the cosine because I like sine better than cosine. All right, now I'm going to do the things with v's. That's a v, that's a v, that's a v, that's a v. So I have sine cubed v. And then I have just a single cosine v. And then dv, du. And what I notice with this double integral is that my two variables v and u are separated from one another, right? They're not trapped together ever. So I can actually use a property from back in the day that allows me to split this into two separate integrals and multiply the answers. So I'm going to do the first integral goes from 0, let's say, to 2 pi. That means I'm doing the one that's dealing with the u's. I'm going to put the u's together. Then I multiply that times the integral goes from 0 to pi over 4. And I'm going to do the v stuff together. I'm almost done. I am almost done because I'm about to realize something. This integral right here, can you tell me the antiderivative of that? Basic u sub. 1/2 sine squared u, right? So I'm just going to come up here with that. That antiderivative is 1/2 sine squared u. That's a basic u sub, right? And I'm going to evaluate that from where to where? 0 to 2 pi. But the value of sine is the same at 2 pi as it is 0. So when I plug in, no matter what happens here, I'm going to get 0 as an answer, right? So this is going to become 0. And if this is 0, then so is that. I mean, well, not so is that. Then the final answer is 0 because 0 times that's going to be 0. So I don't even need to do that integral, although that would be a basic u sub as well. So the final answer is 0. Kind of boring. So if we go back to the top of that ice cream looking thing, what we're saying is that if you were to be on this surface and you were to take every single point, do the x times the y times the z, and then add to it the next x times y times z at every one of these points, it would add up to be 0. Does it make sense to you that it should be that? I mean, it's the symmetry that we have here, yeah?
Density analogy doesn't really make sense anymore.
Density analogy doesn't make sense anymore, does it? Because that would mean you would have 0 mass. Your density function could never be x times y times z. But yeah, you could have like a net heat or something like that. It's colder in this region, above 0, negative and positive temperatures adds up to be. It's like a 0 sum, yeah. I think it makes sense if you think about the symmetry of the problem. It's like when let me move all this stuff out of here. I think that moves everything out, yeah. So if you think about we look at it from the top, because the function is x times y times z, whatever happens in here, isn't your x and your y both positive? And your z comes out at us, right? And that's positive as well. So when you do x times y times z here, your answer is going to be positive, right? And then when you go back in this part right here, you get a negative x, a negative y, right, and a positive z. Won't that be the same as this then? Won't you get the same answer here? But then when you go over here, it's a negative answer, and then over here it's a negative answer as well. So everything kind of, these two cancel out these two. But it's just because of the symmetry of the shape and the symmetry of the x, y, z function. If I made that z squared, well, that probably still give the same thing. If I made that, what would I need to make it? Something not where they're multiplied. If I add x here, there we go. No, you no longer have the symmetry, okay? Yeah, you could have said 0 by not doing any calculus at all, but that would be a specific scenario only. Oh, man. Let's keep going. All right. Some nice results. This is not in the lecture notes that are online. I added this later. So if we look at this surface integral that we were just talking about, surface integral of f over some surface S, if we make this function f of x, or f of x, y, z equal to 1, then it's back in the previous section, which is just surface area. So this is, we've done this before, we've seen this property before. Like if we did a double integral over d of 1 dA, that was the area, right? That was the area of d. We've seen that. We know if we do a triple integral over some solid E of 1 dV, that that's the volume, right, of E. So there's like a theme here, right? If we do the line integral over C of 1 ds, then this is the arc length of C. There's this theme, right? If you have 1 in the integral, then whatever this is with respect to, this is with respect to arc length, that's going to give you the arc length of that curve. If we're doing 1 with respect to volume and we have the solid E, then this gives you the volume of that E. If we have area, right, and this is the region we're integrating over, that's going to be the area of that D. So if we have 1 here and we're doing it with respect to surface area, right, then the surface, this is going to be the area of that surface. Yeah? All right, some other applications, and I'm not going to do any examples, but again, the common theme, if the scalar function in here is the density function, then you can calculate the mass, calculate the mass by doing that integral, and then you can find the center of mass, x bar, y bar, z bar, by computing these double integrals. It's all tied into what we talked about before, right? But now you're talking about a surface with a density as opposed to a curve with a density. All right, we're ready to look at the handouts. The handout that I gave you. So I'm going to bring it up in my notes here because I made a slight change that you're welcome to make as well. Everyone have that color handout? Where the hell is it? Everyone has it? All right, look at the first page. First thing I want you to do, you see the first blue box? Put an A next to it. That way if I want to refer, I can refer back, you know what I'm talking about, all right? That one's A. The next one, Z. No, I'm kidding, B. Right? And just keep going through the document and do all the boxes. C. You should, I think there's what? H? You should get to H. Everyone got it? All right, we are going to be using this handout to talk about surface integrals to start. And then the second part of the handout deals with flux. So for right now, we're just doing surface integrals where we have a scalar function in here. Right? So what you see right here is exactly the formula that I just put up on the board a second ago. The double integral over S of some scalar function f of x, y, z with respect to surface area is the double integral over D, the domain of the vector function that draws the surface, the function, scalar function evaluated along that surface times the magnitude of the cross product of the partials with respect to area. Right? That's the formula we just had. Visually, the surface S lives in three-dimensional space, right? The domain of that, D, right, cannot be visualized. The domain is not here. You don't see it, right? It's like I said, the clock, two clocks in the background, one that runs through the U values, one that runs through the V values, right? So if you want to do that type of integral, where you have your vector function, boom, that's what you do, all right? Now, special cases. Let's look at the next one. What if you're trying to do a surface integral of some scalar function over some surface S, but this time your surface is a function of x and y? That means your z depends on x and y. So there's a special situation where your z depends on x and y. I'm calling it g of x, y instead of f. Why do you think I'm calling it g, not f? Because the f is already taken, right? The f is the scalar function that's given to me, so I can't use f twice. So I'm using g as the part that, the z component of the surface, right, is some function of x and y. So if we go through and calculate this again, this doesn't change, well, this does change, right, a little bit. We're evaluating the scalar function instead of along the vector function, r of u v, the x is just x, the y is just y, and our z gets replaced with whatever that function is. So that's different. And then here, I deduced this for you a second ago, didn't I? I showed you all where this comes from. So that's that same formula. I think I may have rearranged it a little bit, but that's the same thing. So this right here, the square root down, is the magnitude of the cross product of the partials if we're in this special scenario. And here's the picture that goes with it, right? This time your S is some function of x and y. So it's a classic surface from the beginning of this class. The domain can be visualized on the ground as part of the xy plane. That domain might be a type 1, might be a type 2, might be a polar, who knows what it is, right? But it's something we'll be able to see on the ground. Now, I put here why. Why is this formula true? I go through and I actually prove again to you why you wind up getting that thing at the end. Okay, so that's just to kind of like clarify. All you really need to know is this part in blue and the picture that goes along with it. I think if you understand that, you're in business. Okay, let's look at the next special scenario. What if you have a surface, different surface, right? This surface is a function of x and z. So your y is a function of x and z. So this time your surface is coming out the y-axis, right, like this, right? And the domain is projected upon the xz plane. Your domain lives in the xz plane. Then what changes in the integral is that your x stays x, your z stays z, your y changes to whatever function it is. And then in here, this is almost the same thing, isn't it? Like you're just taking the partial with respect to x, partial with respect to z, you're squaring those, adding them together, and you'll always have a plus 1. And there's one more scenario, right? It's where your x would be a function of the other two variables. If your x is a function of y and z, now your surface lives like out the x-axis out here. The domain would be cast upon the yz plane. Then it changes to this. So now your x is replaced with that function. Your y stays y, your z stays z, and over here you do those partials. So do y'all get this, or I mean, yeah?
In the test, will there be a picture of the actual bit that we're analyzing?
Great question. Will there be a picture? I think on the review I do include pictures, right, on some of the problems. So I would anticipate that I will provide pictures on some, not everything, okay? If I feel like it's something where I don't want you to be sitting there trying to figure out what it looks like the one we just did with the sphere and the cone, I wouldn't give you a picture for. But something like the one we're about to do, I'd give you a picture. All right, that's it. Those are the three things. You'll see on the notes now it changes. It says surface integral of the vector field f, right? That's where there's a transition. We're not going there yet, okay?
Okay.
So let's go and do an example now. I would like for us to evaluate the surface integral of f over the surface S, where the surface S is the outer surface of that entire object that you see there. So this surface actually has how many surfaces that make it up? We have this, right? That's 1. We have the green, right? That's 2. And then we have the back part of it, which is the red, right? There are 3 surfaces. So capital S here is all 3 of those surfaces together. Yeah? We have to add them all, which means we have to do 3 separate surface integrals. 3 separate ones. Okay? Now I don't have colors, but let's start with the red one, because I think the red one's the easiest one. Let's call that one S1. So S1, oh, by the way, I would give you all this, right? So you would have this information right here. So S1 is going to be the one where we have x equals 0, just so we're clear. All right. Look at that surface. Can you draw that easily? Is that one of our special cases? And raise your hand. I don't want to just blurt it out. Do you see here, is this A? Is this B? Is this C? Is this D? I didn't put it on mine. Let me put it on mine. A, B, C, D, right? So what do you think? What do you think? You said D. What do y'all think? Is this surface along the x-axis? In other words, projected out. Is the y and the z the domain of that? Yes? The red? The y and the z, the yz would be where the domain of that lives. But it actually lives on yz, doesn't it? It lives on that plane. So I can use case D here, right? D in our boxes. I know that the double integral over S, I don't think I need that, of f of x, y, z, right, d capital S, because we're in the special case, should be the double integral over d of our function, right? Our function, but we will replace the x with what? G of y, z. The y gets replaced with nothing, right? Just y. And the z gets replaced with z. And then here, the square root of g with respect to y squared plus the partial of g with respect to z squared, sorry, plus 1 dA. But what's g? What's the surface? 0, right? I mean, what is this right here is our function, right? This right here, x, our x value, is some function of y and z. It's the constant 0 function. It's super boring, right? It's just this plane. That's all it is, right? So now what I'd like to do is actually plug in. Here's my f function, right? Into that f function, I'm going to replace x with what? 0, right? 0. Because what is x? X is 0, right? So this becomes double integral over d of 0, and the rest doesn't matter, does it? The rest doesn't matter. Who cares? The answer is 0, right? So there's no contribution along that back side because it just turns out that our scalar function asked for x, and along that back side x is 0, so we get nothing. Yes?
Could you make the case again, like from the previous problems of symmetry, if you were given something like that?
Well, well, I mean, it's not necessarily, I don't know, it depends on how you want to talk about symmetry. Are you saying symmetry because it's a circle or symmetry? Because it really actually wouldn't matter what this surface looked like. It could not be a disk. It could be real wonky looking like this instead of that disk, and I would still get 0 because the scalar function is 0, right? If I were just flat up against the xz plane, no matter what the shape was, plugged in there, it's going to be 0. So I don't need symmetry at all for that, right? I mean, I think you could make an argument for symmetry here, but it wouldn't be required.
From quadrants. You broke the last
Yeah, yeah.
one from quadrants. Let's make that argument for this one too.
You could, but I think you wouldn't. It's not a necessary condition for this to be 0. All right, we good along S1? All right, let's do S2 now. So which one do y'all want to do for S2? I like the blue one for S2. Because it's also kind of a disky looking thing, isn't it? It's kind of disky, just tilted. So let's go with S2 here. For S2, we are looking at x equals 1 minus z, right? Hey, wait a minute. That's a special case as well, because I can see clearly here that x is a function of 2 variables, y and z. Well, in fact, it's only a function of one of them, but I could argue that there's a y in here. There's 0y, right? Plus 0y. So do you all agree that x is some function of y and z right there? And so I can use that same formula I just used, the same exact one. It's going to be double integral over d. I'm using this formula, this is box D, right? Sorry, I should have put that. That's box D on our sheet. And then it's going to be the function, I'm going to put it here, the function with your x replaced with g of yz. Your y is going to stay y, your z is going to stay z. Then we're going to have the square root of partial of g with respect to y squared plus partial of g with respect to z squared plus 1 with respect to area. Double integral over d. All right. My scalar function f is just x, right? And I'm replacing x not with 0 this time, but with what? 1 minus z, right? 1 minus z. So this piece right here is our x up there replaced with what we're saying x is, which is 1 minus z. Okay?